So a flow leader basically is an area in the part that you purposely make thicker in order to promote flow. And on the flip side of that, a restrictor is an area where you thin the wall out to restrict flow. And there are several different reasons why you would do it, but usually it's to balance the flow out in the case of flow leaders, or in the case of restrictors, it's usually to prevent a backfill situation. So the reasons you would do flow restrictors or flow leaders would be, like I said, to balance the fill. So in those cases, you may want to balance the fill in order to improve the packing conditions, to make shrinkage more uniform across the part so that the part packs out more uniformly. If the part packs out more uniformly, you have a better opportunity to have more even shrinkage, and more even shrinkage leads to less warpage. So that would be flow leaders. For restrictors, well, I guess to add to flow leaders, you might want to put flow leaders in to control your knit line locations. So in highly aesthetic parts, you may not want a knit line to be visible in certain areas. So you would, and if it can't be controlled through gate locations, you may want to use flow leaders to do that, or flow restrictors. And then mostly flow restrictors are used, like I said, to prevent backfilling. If you have backfilling in a plastic part, what it'll do is trap air, and trapped air compresses. Compressed air superheats, and it may cause a void in the part, or it may burn the part. Some of the limitations of flow leaders and restrictors are either making the part too thick or too thin. If you go too thick with a flow leader, and that's the only way to get the kind of filling pattern you want, then you get into situations where you may have some aesthetic issues on the show side of the part, where you have gloss differences, for example, or you may end up with some sink marks. On the cooling side of things, you may end up with a section that's so thick that it now controls your cycle time. So it may introduce some additional cycle time that you weren't prepared for initially. On the restrictor side, if you make something too thin, again, gloss differences can show up at the transition. So. I've been to mold trials where guys have just gotten in there with a grinder and start grinding material out kind of haphazardly, which is no good. I mean, it looks messy, it is messy, and there's no real thought put into how much material should be removed from the B side. The next approach would be just to go trial and error, back and forth between mold trial, back to the mold maker, remove a little more material, try it again. If it works, great. If not, you got to go back to the mold maker. Not a bad approach, but you know, it takes time and effort to do that, which when you're at the point where you're trialing the mold, you don't have much time. So that's the second approach. But the best approach is to go to simulation. I mean, simulation, you can do all that trial and error in a quote-unquote software prototype before you even cut any steel out of it. So you know exactly how much you need to remove to get the job done. So most of the time when people think of flow leaders, they think of increased wall thickness in the part cavity itself. But actually you can do balancing upstream for multi-cavity or family molds by increasing runner sizes or decreasing runner sizes in select areas of a multi-cavity mold. So in the case of where all the parts are the same, they may not be geometrically placed the same distance from the center of the tool. So in those cases, you would take the secondary runners, change the runner size to each of those cavities to make one area, enhance the flow to that cavity so that it balances out with the other cavity. So that would be a non-naturally balanced mold. In the case of family molds rather, where you have one large part over here and a smaller part over here, you can do the same thing. Change the runner size that leads to one cavity and enhance the flow and make it fill out at the same time the smaller cavity fills out. So by doing so, you balance the flow, not only the flow, but the packing of the two parts, and you will generally have more uniform shrinkage between the two cavities. Generally speaking, it should be used as a last resort. Whenever we can, we use simulation to solve a warpage problem or a flow problem by changing the mold design or changing the processing. Those are the first two things that we go to try to solve problems, because if we have to go back to the part design, it usually makes the mold more sensitive to processing or mold design changes. So we do what we can to change or to improve things with the mold design or the process, and if we can't, then we'll start looking at things like flow leader solutions and changing around wall stocks and so forth until we get the filling pattern that we want. But to the extent that we can, we try to do that with mold design and process.